Okay, last video on chapter 6 and a few definitions about upper level winds. So one of our first definitions is for zonal winds. And zonal winds are prevailing westerly straight line winds on upper level maps. You see it highlighted here. They are going to move straight from west to east, zonal winds. They tend to clear out surface storms rapidly because there is nothing that's impeding them at all. They tend to move fast, have high speed winds, and clear out those storms. As opposed to meridional winds, which are winds that follow the longitudinal meridians from north to south and south to north. You see them here highlighted. Very common off the west coast of the United States, and these tend to throw a kink into the upper level maps and a trough into those maps, and also give a detour to winds. And in giving that detour, it slows the winds down by taking that extra measure, and it puts in place a pattern that can intensify surface storms rapidly, because the surface storms slow down and start to really mull and develop. We will be looking into cyclonic storms and the impact of these meridional winds on cyclonic storms. And in addition to that, those upper level winds also can have higher speeds when the contour lines are tight, and you notice that here, and they can have lighter speeds when the contour lines have a lot of distance between them. Now you may say, boy, that sounds an awful lot like wind speeds at the surface with isobars, and the analogy that we were looking at in regard to the lake, which has a real low flow and a lot of distance between the shoreline, and then the stream, which has a real short distance between its shorelines and the faster flow. That's where you get the babbling brook from. It's not the change in elevation. You could have the lake and the brook on the same elevation, but the brook would babble because of the faster flow between those two distant shores. So again, to just review this, pressure gradient force is pressure change over distance. When you have narrower distance, that means the pressure gradient force is going to go up because you have a smaller denominator that makes a higher quotient. And you might say to me, but wait a second, there are no pressure changes on an upper level map. And you'd be right, there are no pressure changes on an upper level map. So why would differences in contours reflect pressure gradient forces? And why would small contour differences and tight gradients produce high winds? And you would be very right to ask that question in regard to the map. To give you a better idea of the horizontal pressure gradients in the upper levels of the atmosphere, because it's not as cut and dried as on the surface where everything's at one level. Now we have many levels, 750 millibars, 500 millibars, 300 millibars, 200 millibars, 100 millibars, and they are still communicating with each other on a horizontal basis to move air horizontally in the upper levels. So I took these two pieces of artwork and I shifted them to give you a better feel for that. And let me walk you around them a bit. I moved the south down, I moved the north up, I moved the south down here and the north up here. Here I have the surface of the earth, kind of tilted. Think of it like a mountainside, okay? Kind of tilted there, and I have the upper atmosphere above it. And I have some of the other upper level surfaces there. I have a 500 millibar surface here, and I have a 300 millibar surface above it that I drew in. Now, all of these surfaces are fine, and they really signify and bring to light the inequalities of the areas in the upper atmosphere. And we go back to the second law of thermodynamics, saying that every system seeks equilibrium. Well, if I have a 500 millibar system that is up in Mexico and down in Canada, and I have a 300 millibar system that is riding over it, there is a point where on the horizontal plane, the 500 millibars is greater than the 300 millibars. And that is a system that would seek equilibrium in a horizontal plane. Let's look at it here. Here's my 500 millibar surface, and I'm moving from warm air at a higher pressure to cool air at a lower pressure. And I am hitting the 300 millibar surface very quickly because of this drop in altitude. This 500 millibar surface took a real profound drop in altitude along with temperature. Remember, they go together, pressure and altitude. And in doing so, it has a big difference between 500 millibars and 300 millibars right at the same horizontal level. That big difference is going to seek equilibrium quickly, meaning that air is going to move rapidly, meaning that's going to produce a real pressure gradient force there. And that fast pressure gradient force is going to move from south to north and then get pulled by the Coriolis effect to the right. And that's going to end up as a westerly wind, just like you see it here as a westerly wind in the purple. So that wind speed really moved up, and you see my barb here. Get my mouse back. Here's my barb here that shows a wind speed of approximately, holy cow, 50, 60, 70, I think we're looking at least 85 miles an hour or 85 knots up there, 85 knots up there at that 500 millibar level. In here, when I have had a steep temperature drop and a steep altitude drop in my surfaces that make up my contour lines. And let's look at the contour lines. What I'm looking at with this real sharp difference in altitude, I am looking at a contour line that varies between 5,580 meters and 5,520 meters. Okay, real tight there, and that's the altitude drop. And on the other spectrum, I could look for a much more gradual wind speed here that is associated with a broader contour interval. This contour interval is at 5,640 meters to 5,580 meters, about 140 meters there. Yeah, about 140 meter drop. But it's over a longer distance. And in fact, I'm representing that here, this longer distance. It's not exact what I'm showing to you here, but I think you get the picture that when I start at a higher altitude and I don't have a big altitude drop, that means that I have an equilibrium that is slower to move. And so this is slower to move and change. And when it is slower to move and change, that means it is a slower wind speed. So I hope that helps you. All of these will be pulled by the Coriolis to the right, but it's the speed change that we're talking about. And I also wanted to bring in the upper level map again to show you that when the gradients are tight, you're getting strong winds right in through here. In fact, I have the meters here, 5,580, 5,520. They're right along in here. Really tight gradients in here and strong winds. And then when these gradients start to open up, particularly around here and particularly up here, when those gradients start to open up, there's a more gradual change in altitude of these surfaces, one on top of the other, and you can equilibrate the differences in pressures among those different surfaces at a slower rate over a larger distance and over a slower wind speed. And I want to give you one other cool rule of thumb that has to do with wind speeds in the upper atmosphere. The rule of thumb is this: if you're looking for your next storm, then you need to look for the low pressure system that is around you. In looking for the low pressure system around you, look at the clouds. And when you look at the clouds, you know those clouds are in the upper levels. So you know that those clouds are going to follow a geostrophic wind that is pushing them. So if you get yourself in the position where you are chasing the clouds, then you know that you are going in the same direction as the geostrophic wind. If you are going in the same direction as the geostrophic wind, then you know that the pressure gradient force has gone from the higher pressure to lower pressure, and you know, if you're chasing after the wind, that the low pressure system is to your left. So this is a way for you to know that as you're running with the clouds or walking with the clouds, the low pressure system is going to be on the left. And you have a representation of that in your book about riding along with clouds. And I'm not saying that this guy is really at the right angle, but riding along with the clouds, he's riding with the low pressure system to his left. And I hope that will help you to find the next low. Let's go on to the next chapter.